Up to this point, we've discussed Lewis structures, which tell us the connectivity of atoms, and the Vesper model, which helps us to predict the 3D shape of a molecule. We've not yet made any attempt to explain how the bonding occurs. We have discussed for a while now that covalent bonds occur when electrons are shared between atoms, but we haven't explored how the sharing happens. That's what we'll examine in our discussion of valence bond theory. The main principle of valence bond theory is that bonds form when occupied orbitals overlap. This may involve atomic orbitals. This just means the s, p, d, and f orbitals we've explored already, or those atomic orbitals may be used to form mixed or hybrid orbitals. Effectively, valence bond theory is a quantum mechanical description of the distribution of electrons in bonds. By this, we mean we are looking at electron locations, this time in bonds, in terms of probabilities, in other words, through orbitals. The H2 bond forms when the 1s orbital containing an unpaired electron of one hydrogen atom overlaps with the 1s orbital containing an unpaired electron on another hydrogen atom. When orbitals overlap head-on or directly in the internuclear axis, we call the resulting bond a sigma bond. The internuclear axis simply is the axis that runs between the two nuclei of the atoms involved in the bond. The name of the sigma bond comes from the notion that if we rotated the bond around the internuclear axis, then it would look the same no matter where we stopped. My apologies for this horrific rendering of the images shown on slide 25 of your lecture slides. You probably should get out those lecture slides and take a look as you try to work your way through what I'm talking about on this slide. All single covalent bonds are sigma bonds, and we can form them in a variety of ways. On the previous slide, we showed a sigma bond formed between two s orbitals, but we also can have head-on or direct overlap in the internuclear axis between an s orbital and a p orbital, shown here with the HCl bond, or between two p orbitals, shown here with F2. There are a couple of important distinctions to make here. The first is that the coloring of the p orbitals indicates phase. For a 2D wave, this would be sine and cosine. For a bond to form, the overlap of orbitals must be in phase, in other words, red to red or blue to blue. In other words, this is constructive interference, just like we talked about back in Chapter 5. The second item of note is that p orbitals come in sets of 3. Only the p orbital that is oriented in the internuclear axis can be involved in a sigma bond. Of the x, y, and z axes, most chemists call z the internuclear axis. So technically we would say that we are looking at an s orbital to a pz orbital or a pz orbital to another pz orbital. Usually I just call it, very scientifically, the sideways p orbital. I don't really care particularly that you know that it's called the pz, but I do want you to know that only the p orbitals that are oriented along the internuclear axis can be involved in sigma bonding. We'll find that the ones oriented perpendicular to the internuclear axis are involved in a different type of bonding a little bit later on.